Have you ever wondered how scientists really know if a new drug works? I mean, they don't just guess, right? Well, they use this incredibly powerful tool called statistical hypothesis testing. And it's basically a formal process for figuring out if what you're seeing is a genuine breakthrough or just random noise. Okay, let's make this real with a super high stakes example. Imagine a company develops a new vaccine. They run a trial, and yeah, some vaccinated people stay healthy, but some still get sick. So what's the verdict? Is the vaccine actually working? Or are the good results just a fluke, just random chance? I mean, with lives on the line, we absolutely have to be sure. See, we can't afford to just guess here. We need a solid, structured way to make the right call. And that, right there, is exactly what statistical hypothesis testing is all about. It's a formal framework for weighing the evidence and reaching a conclusion that's based on logic, not just a gut feeling. All right, so you might be thinking, why can't we just, look at the data and make a judgment call? It's a fair question, so let's dig into why we need something way more formal and why it's so essential. Okay, the core problem, the big challenge, is variability. Think about it. Everyone's body's different, right? Exposure levels change. Data is just naturally messy. And that's exactly why your cousin's story about feeling better isn't enough. Anecdotes just aren't evidence. We need a reliable method to separate the true signal, the vaccine's actual effect, from all that random noise, especially when the stakes are this high. All right, at the very heart of every single hypothesis test is a showdown. It's a battle between two competing ideas. So let's go ahead and set the stage for this scientific debate. The best way to get your head around this is to think of it just like a courtroom trial. Seriously, in a trial, what's the rule? The defendant is presumed innocent until proven guilty, right? Beyond a reasonable doubt. Well, hypothesis testing works the exact same way, but for a scientific idea. So in our scientific courtroom, we've got two opposing statements. On one side, we have the null hypothesis, or H0, as you'll hear it called. Think of this as the presumption of innocence. It's the skeptical view, the default, the status quo. And on the other side, we've got the alternative hypothesis, or H1. This is the exciting new claim that we're actually hoping to prove. So let's talk about the null hypothesis, H0. This one always, and I mean always, represents the kind of boring reality. It's the nothing to see here, folks position. For our vaccine, the null hypothesis would be the vaccine is totally useless. It has absolutely no effect on infection rates. And this is the idea we have to presume is true right at the start of our trial. Now for the exciting part, the alternative hypothesis, H1. This is the claim we're actually trying to prove. It's the whole reason we're running the experiment in the first place, right? In our case, it's the big statement, the vaccine does work. It has a real measurable effect on infection rates. So our entire goal is to gather enough evidence to throw out the null and say, yep, we're going with this one. Okay, so we've got our two competing claims ready for their showdown, but how do we actually use the data, the evidence, to decide between them? Well, this is where the star of the show makes its grand entrance, the p-value. So, after we run our experiment and collect all the data, we have to ask one very, very specific question. It goes like this. If we assume the vaccine is useless, if we assume that null hypothesis is true, how surprising are the results we just got? What are the odds we'd see this exact outcome just by pure random luck? And the answer to that critical question is the p-value. It's just a number, somewhere between 0 and 1, that literally measures how surprising our results are. I like to think of it as a surprise-o-meter. A really small p-value means our data is super surprising, if the null hypothesis is true. And if something is that surprising, it might make you think, maybe that null hypothesis isn't true after all. Okay, check this out. Here's the evidence from our hypothetical trial. You can see the infection rate in the group that got the real vaccine is clearly way lower than the placebo group. I mean, that looks pretty promising, right? But here's the million-dollar question. Is that difference big enough to be truly meaningful, or could it just be a lucky roll of the dice? To answer that, we run the numbers and calculate our p-value. For this hypothetical data, let's just say the calculation spits out this one number, 0.03. And believe it or not, this single figure summarizes all the evidence we just gathered. So what in the world does a p-value of 0.03 actually mean? It means this, and this is the key takeaway. If the vaccine were completely and totally useless, there would only be a 3% chance of seeing a difference this big, or even bigger, between our two groups, just from random luck. Now, a 3% chance, that's pretty small, right? our results are looking really surprising under that initial presumption of innocence. Okay, so we've got our surprising evidence in hand. Now we need a rule, a framework for making the final call, the big verdict. Do we reject the null hypothesis? Turns out there are two main ways to approach this decision. First, we've got the classical approach, which is all about setting a really rigid standard of proof before the test even begins. And then there's the more flexible p-value approach. So the classical approach is super strict, almost like a pass-fail system. Before you even start the experiment, you decide on a cutoff for what you'll consider reasonable doubt. We call this alpha, and a really common one is 0.05. If your p-value ends up being less than that alpha, boom, you reject the null. Simple. The p-value approach, on the other hand, is a bit more nuanced. It just reports the exact p-value, in our case 0.03, and lets the researcher, or you, interpret just how strong that evidence really is. But here's a crucial reality check. No test is perfect. Ever. No matter what verdict we reach, there's always a chance we got it wrong. And what's great about statistical testing is that it forces us to be really honest and upfront about those risks. And this brings us to a really key point about the language we use. You'll notice it's very careful. We never say we prove or accept the null hypothesis. It's just like in a courtroom. We don't declare a defendant innocent, do we? No, we find them not guilty. Same idea here. We simply fail to reject the null, which basically means we just didn't have enough evidence to convict it. So when we make our decision, there are 4 possible outcomes. You can see them laid out here. 2 of them are correct decisions, which is great. That's when we correctly say a vaccine works when it really does, or when we correctly say there's not enough evidence for a useless vaccine. But the other 2 are errors, and we really need to understand these, so let's take a closer look. First, you have a type 1 error. Think of this as a false alarm. It's when we reject the null hypothesis, but it was actually true all along. For our vaccine, this is a big deal. It means we approve a vaccine that is totally useless. Then you have a type 2 error. I like to call this a missed opportunity. This is when we fail to reject the null hypothesis, even though it was false. In other words, we had a life-saving vaccine right in our hands, but our test just wasn't sensitive enough to see its effect, and we threw it away. And this all brings us to one final really crucial concept: power. What is the power of a test? It's its ability to avoid that missed opportunity, that type 2 error. In other words, it's the probability that your test will correctly spot a real effect when one actually exists. So the goal of any good scientist is always to design a really powerful experiment, one that's sensitive enough to find the truth, whatever it may be. And this is where it all comes together, you see. For our vaccine, a false alarm, a type 1 error, means we approve a useless drug. Not great. But a missed opportunity, a type 2 error, means we throw away a potentially life-saving one. So I'll leave you with this question: which mistake is worse? Understanding that trade-off, that balance, is the key. It's how scientists design better experiments, how they make smarter decisions, and ultimately how they turn raw, messy data into knowledge that can literally change the world.